Hello students, today I will discuss another topic of the propositional logic, one of the most important topic, that is the predicates and the quantifiers. Now why we will discuss this chapter, not only that is it is in our syllabus, but what is the main fundamental thing behind this, that we know in case for the propositional logic there are some restrictions. What are the restrictions? That propositional logic that we have studied earlier cannot adequately express the meaning of all statements in the mathematics and in the natural languages. Why? Let us have some example, like say every computer connected to the university network is functioning properly. Now, can anyone say that this statement is always true, or this statement is always false? So such type of statements which appear in frequently in case for the logic problems cannot be answered very clearly with the help of the concept of the propositional logic that we have learned in earlier section. So here we will discuss about some more advanced type of logic, which is nothing but known as the predicate logic, and the total thing we will discuss sequentially. Now, first thing, what is the predicate? So to understand what is a predicate, let us consider an example. Say, let us consider the statement that x is greater than 4. So here we can see that this statement can be decomposed into two parts. One is the x and other is the is greater than 4. So here we can see that x is known as called the subject of this statement, and is greater than 4, that is the rest of the portion, is known as the predicate. So what is the predicate? In general sense of the definition, we can declare in a sentence the words which describe the nature or the properties of a subject is nothing but known as the predicate. Sometimes we denote this predicate as a function of x, because x is greater than 4. So if you put 5 here, so 5 is greater than 4, this statement is correct. But if you put 3 here instead of x, then 3 is not greater than 4, so it becomes false. So this total statement is nothing but depending on some variable x. So we denote this type of statement as a function of x. Say the function of x is written as p of x, and what is the statement? That is x is greater than 4. That I have already told you that here we can see p5, p6, p7 all are true, but p0, p1, p2, p3 etc. all are false. Such type of function px are known as the predicate function or the propositional function. Now what is the quantifiers? Quantifiers is nothing but some assignment values to the propositional function px that makes propositional function to a proposition. From the function we are getting a proposition by assigning some values of the variable x inside of px. Such type of thing is nothing but known as a quantification. That is the way of creation of a proposition from the propositional function px is known as a quantification. And here this area is totally discussed about the predicates and its nature, as well as combined with the quantifiers. So this area is known as the predicate calculus. Now to go for the predicate calculus, we have to define a domain or the universe of discourse. So what is a universe of discourse? That is the all set of possible values that we may substitute in the place of the variable x in the propositional function is known as the universe of discourse. Okay. Now generally, depending on the universe of discourse, the quantifiers is divided into two parts. One is the universal quantifier and another is the existential quantifier. What is the universal quantifier? Suppose you have a domain D on which you can choose all values of the variable x, and you put the values of the variable inside the propositional function px, and you can see that px becomes true for each and every value of x lying in the universe of discourse. So this type of statement is nothing but known as the universal quantification of the propositional function px. And what is the notation? The notation of the universal quantification is nothing but for all x px. So whenever you see this symbol for all x, you remember that it is nothing but representing a universal quantifier. Okay. Now, similarly, what is an existential quantifier? Say we can say another statement. It may possible that there exist some values of x present in the universe of discourse for which px is true, and for some values of x px is not true. We will find out those values of x for which px is true. If we can say there exists at least one values of x in the universe of discourse for which px becomes true, then such type of case is nothing but known as the existential quantifier. And what is the notation? That is, there exists x px. So whenever you see there exists x px, you remember that it is nothing but representing the existential quantifier. So let us have a look in the following problem. Say we are taking the set capital S equals to 1, 2, 3, 4. That is our universe of discourse. Okay. Now we are taking another propositional function px. What is the propositional function? X square is less than 10 for each and every x belongs to S. So here we can see that for 1, 2 and 3 the statement is true. But whenever you put x equal to 4, it becomes 16, which crosses 10. So the statement is getting false for the value of 4. So here we can declare that for all values of x present in the universe of discourse, this statement is not getting true. Therefore, we cannot apply for all x px here. So for all x px, p1, p2, p3, p4, all their conjunction must be true. Otherwise, for all x px is not true. But simply think about that. This statement is true for 1, 2 and 3. Therefore, we can say there are some elements present in the universe of discourse for which this statement is getting true. Therefore, we can say it is nothing but an existential quantifier. That is, there exists x for some values of x present in the universe of discourse, px is getting true. Okay. Now always remember that whenever we want to calculate, that is whether it is a existential quantifier, whether it is an universal quantifier, we have to remember this one. Say if capital S is the total set of universe of discourse, x1, x2, xn be the number of elements present in the universe of discourse, and we have to check whether for all x px is true, we have to find out all the propositions and their conjunctions at each and every point. That is, p at x1, p at x2, p at xn, all their conjunction is getting true or not. If all their conjunction is getting true, then we can say that for all x px is true. But in case for the existential quantifier, we need only one value of x for which px will be true. Okay, so for that case, we will not take the conjunction, we will simply take the disjunction. That is px1 or px2 or pxn. If any one of the statement is true, then there exists px is true. Okay. Now let us have a look for another example. We want to convert it into the universal or existential quantifier by the statement. How? Say px is a statement given that x is a good batsman, and let the universe of discourse be thus all students in the class. So if I want to say that for all member of the class, if the px is true, and we want to apply that for all x px, that will mean that every student in this class is nothing but a good batsman. But if we want to say that it is an existential quantifier, then how we will write down it? We will write down it by at least one student in this class is a good batsman. These are the most important topics. Together with this topic, we will again solve some logical validity of the statements that we have done in the previous lecture note. We will simply solve those problems with the help of the quantifier, but in the advanced level. So we have to remember how we have to write down the quantifier, how the statements are related to the quantifier, like this. Okay. Now another thing I want to express here, the binding variables. For our WBT syllabus, basically short questions type problems that appear from this small portion. What is the binding variables? Whenever you apply some quantifier to a variable, then the occurrence of the variable becomes a bound. It cannot go beyond the quantifier. So that variable is nothing but said to be a bound variable. But in the quantification, if there are some variables left on which you are not applying the quantifier, then those variables are said to be the free variables. And what is the scope of the variable or quantifier? The logical expression on which the quantifier is applied. That is nothing but the scope of the quantifier. From here, basically short questions are appearing. Okay, so here I am writing down some propositions, and we are find out the bound variable, free variable, and the scope of the quantifier. Okay, so if I am writing down for all x px, you can see that x is our variable, and for all x is present here, that means universal quantifier is appearing. That means universal quantifier is applicable on which part? It is applicable on x part. So x becomes the bound variable. There exists no other variable present in this proposition, so there is no free variable. And what is the scope of the variable? For all x, that is the quantifier, is applied on which propositional function? It is applied on the px. So what is the scope of our universal quantifier? That is px is the scope of our universal quantifier. Similarly, if we go to the proposition for all x, px and qx, so here also we can see that x is our variable, and for all x is our universal quantifier. It is applicable on what? Px and qx. So x becomes the bound variable. Also there is no other variables left, so there exists no free variable. And what is the scope of this universal quantifier? This universal quantifier is applicable on px and qx, so the scope is px and qx. Similarly, if we take there exists x, pxy and qx, so here we can see it is a double variable function, p, x and y, but the existential quantifier is nothing but depending on x only. So the bound variable become x, but here y is become free, so the free variable becomes y. And what is the scope? On which part there exists x is applied? Px, y and qx. So the scope of the variable becomes px and qx. Y becomes the free variable. Similarly, for this one you can also observe this. Now the next property is that the negation of a quantification or quantified statement. To understand this, let us simply take an example. Say every student in this class has taken a course of the discrete mathematics. So obviously we can see every student is present here, that is, it is stating all students in this class have taken the course of the discrete mathematics. Therefore this statement is nothing but gives us the universal quantifier. So we will write down it by for all x px. Okay, now if you want to make the complement of this statement or the negation of this statement, how the negation will be there? Simply think about that. What will be the negation of this statement? That is, every student in this class has taken a course in the discrete mathematics. So the negation will be simply, it is not the case that every student in this class has taken the course in discrete mathematics. That is the negation. This statement is also equivalent to what? That is, there is at least one student we can see in this class who has not taken the course of the discrete mathematics. So this statement, every student in this class has taken a course of discrete mathematics, the negation of this statement actually becomes there exists at least student in this class who has not taken a course of discrete mathematics. So if you take a course of discrete mathematics, then that is the statement px. But if you are not taking a course of discrete mathematics, that means there exists px, complement of px, not taking the course of discrete mathematics. You are saying here there exists a student or there exists at least one student, so there exists x complement of px. So actually if we want to make the complement of for all x px, we are getting this statement. So here we have the statement that is negation of for all x px, it will be logically equivalent with what? There exists x complement of px. Okay. Similarly, if we want to take negation of there exists x px, it will be for all x negation of px. Now let us do some examples. Say, what is the negation of this statement? There is an honest politician. So we are considering say hx be the statement x is honest. So the universe of discourse for this problem is nothing but all the politicians in this world, and I am saying that there is an honest politician. That means there exists x, hx is true, x is honest, that we have already declared. So there exists x, hx is true. Now if we want to make it the negation of there exists x, hx, already we know that negation of there exists x px equivalent with what? For all x negation of px. So similarly it will become for all x negation of hx according to this formula. And what is the statement of this one? For all x negation of hx. Negation of hx means what? X is honest is hx. Negation of hx is x is not honest or x is dishonest. So what will be the statement? That all politicians are not honest. Okay. Similarly, go for the another problem. Say, what is the negation of for all x, x square greater than x? So simply we can apply this formula that negation of for all x px is nothing but there exists x negation of px. So here we can see negation of for all x, x square greater than x is logically equivalent with what? There exists x negation of x square greater than x. So if x square greater than x is our statement and we want to make it negation, what will be the statement? Just the complement, that is x square is not greater than x. That means x square must be either less than x or it may be equal to x. So the statement will be there exists x, x square less equals to x. Okay.